Yes, good evening everyone and welcome to this today's session of Saturday Talk. We are privileged to have Padmashree Dr. Gnanagandhi today. A brief introduction, though he is repeating in this session series for the new joiners, his introduction is there. An eminent personality in the area of cryogenic rocketry, Mr. Gnanagandhi took his graduation in mechanical engineering from Jayagarajar College of Engineering, Madurai, and joined Aero in the year 1968. He has contributed in the area of rocket propulsion widely, covering solid, liquid and cryogenic rockets for the last 38 years. Mr. Gandhi has served Aero in various responsible positions like Project Director, Program Director, Cryogenic Systems, Projects and Associate Director, Liquid Propulsion System Center. In recognition of his contribution to India's space program, Shri Gandhi was given ASI Award 2002 by President of India, Government of India, has also honored Shri V. Gnanagandhi with the Padmashree Award for his outstanding contributions to ISRO and our country in the area of launch vehicle development with particular attention to the most complicated cryogenic rocketry. He also obtained Performance Excellence Award in ISRO in the year 2007 awards. He is involved in the realization of hydrogen bus with Tata Motors and has conducted the first trial run. His strengths are giving lectures on rocket propulsion. At present, he is associated as the Senior Vice President, Propulsion at Skyroot Aerospace as well. And today he is going to speak on additive manufacturing for aerospace components. Over to you, sir. Thank you so much.
Well, I have taken this topic because after my retirement, maybe ISRO, they didn't allow for quite some time, 4 or 5 years I was there, up to 65 or 66. Then as he said, I started working ISRO and Tata. We run the hydrogen bus, first bus. And now everywhere I think a lot of people, they are working on hydrogen bus and vehicles and other things. Well, sometime I thought, some more than 40 years, my wife was cooking for me. Then I thought, why not I will cook for her. A few years, I tried that also. So one of the Hindu paper competition, I participated and I won the one of the competition. They selected me also one of the good recipe I have given. So like that, I spent my time, maybe about 7 years back. One of our ISRO young engineer, he asked me, why don't we join with me, sir? I am going to start a startup company to launch a small scale rocket. Then I asked, I was laughing. It is very, very complicated. How are you planning to do that? So second time, so I could convince he has some good long-term vision. So I said, okay, I will also join with you. So like that, I started my career in Skyroot in 2017. For the last 8 years, I am there. Mainly, I am looking after the liquid propulsion, mainly at storable as well as the cryogenic propulsion system. And first flight, what we are planning this year before December, is storable and 2 or 3 places. So when I see in ISRO, when something is working, we will not modify or we will not do anything. But this particular gentleman, my boss or CEO, young man, he said, sir, forget about the old things. I want a cutting edge technology to be used. Today's trend and whatever things has to be done. It was fascinating, but I thought whether he is right or not, and I was debating. Because most of the components, what I know is bracing technology and that and welding, EB welding and all those things. So first itself we said, these are all our thrust chamber or injector has to be 3D printed. Well, what is 3D printing? I started looking into that. So maybe I know that time, maybe about 30 or 35 years back, Anna University in CAD/CAM center, they invited me. They asked, why don't ISRO fund some money? We want to do a 3D prototype, fast prototype machine to buy using wax machine. And with with that, we can give you a lot of samples and other things. You can predetermine the tolerances, this, that. So, okay, I said, okay, we will also give some money. So almost like 10 lakhs or 15 lakhs from ISRO we have given. TVS also they funded, and one of the university, Crust Engineering, if I'm correct. So we three funded and we got the machine. So at that time itself, I involved a little bit on 3D printing, but that was not metallic. That was non-metallic, and we could print some of the components, very critical ones and other things. It was very useful. But currently, now we have to start with the metals. That too with superalloys like titanium or inconel and stainless steel and some of the aluminum components also. So our environment, especially in the rocket engine, it is very, very difficult in the sense the inside temperature is nearly about 3000 degrees Celsius, and no metal can withstand that kind of a temperature. So we have to find technique. So generally it will be a double wall. So I will explain a little later how it works. So that particular engine, even though it is small, and because of our CEO, we want to do it only by 3D printing. So we started searching who are all the good people in India. So very few people at that time, maybe about 6 years back. Now, of course, we have many institutes. They have come up with a lot of 3D printing machines. One is Wipro, and another one is in Pune, Amit sent. So I went to Pune and discussed with him, and I asked him whether it is feasible. Then you may ask, why do you require, first of all, this 3D printing for our aerospace? Maybe as I said, it is normally, even though it is additive manufacturing, some people call it 3D printing or layer by layer printing and other things. There are mainly 2 or 3 ways. One is direct deposition technique, that is one, or wet fusion technique, or electron beam technique, or deposit. So EBM or SLM, okay, this is selective laser. We call it wet. For wet itself, we fuse the metal. So we call it wet fusion technique. So the particular gentleman in Pune, he was having only one machine and he has vast experience in that. So he said, sir, you give me a trial, I will try to do the work. We said, fine. So this additive manufacturing is opposite of our machining. Normally, if you want to machine a small flange or a nipple or an adapter or anything, you take a rod or a small or a cube or anything. So we will remove the metal. Finally, you will get the product, right? Lathe or milling machine or any other this thing, or you remove it. But in additive manufacturing, it is in the opposite. That is layer by layer, we add the metal and bring to the final product. The final product is only in the 3D model, not on 2D drawing and seeing, and technician is going through or 1 millimeter or half a millimeter. Nothing. Everything is in the 3D format. So why aerospace is very keen, very important thing is weight reduction. We can go for exotic materials which we cannot weld or which cannot form, but that can be easily printed, specifically titanium or inconel. And the time taken for producing this type of components are very, very less compared to the nominal. Maybe I will explain it later how much I have taken and how much this thing. The faster turning around for the parts or repair work or whatever you want to do, this was very much handy. So everybody now towards, especially specifically for smaller thrusters, worldwide, people are going for 3D printing engines. Maybe the benefits are, as I said, the reduction. Even in some places, we could get more than 60%. Even very complex internal designs. Maybe I will show you one of the injector, how the internal structures are there. We may require almost like 15 parts, which has to be either welded or screwed or braced type of thing. In one stitch, we can do it here. So that is very, very important, that complex internal structures can easily we can make. And material efficiency, of course, reduced waste in subtractive method, that is a machining method, we lose a lot of materials. You may take 20 kg and finally your product may be 1 kg. But here, it is not like that. You may take 2 kg, you may get 1 kg product. Why that also 2 kg, I will explain it later. So like that, we have a lot of this thing. As I told, many parts can be reduced. So fewer joints, reduced assembly time. So one injector, earlier we may take 2 or 3 days to assemble. Now it is already assembled form we are getting. So that kind of flexibility we have. So the major process which involves in component making, first of all, the AM design itself is slightly different from conventional. Suppose if you want to make an injector or a thrust chamber or a component or any body, anything you want to make, you have to think, because this is layer by layer in this form. So forming time, if any taper, if it is more than 45 degrees, if it comes, a lot of support is required to hold the layer. So then it will be a little difficult. Then corner radiuses, or maybe a square where it is coming and meeting very perfectly like that. So there are joint points that has to be done. Now, of course, a lot of DFAM softwares are available. That also now the people started using. Once the design is over, it is fed to the machine, where the process parameters, this is one of the very, because this is process oriented, maybe there are a lot of gaps or disadvantage. Maybe I will touch a little bit towards my end of the talk. So metal in the feed is only a powder, and whatever the material is required. For example, you take titanium, we have full alloy as well as half alloy. Aluminium is 6Al4V is called the full alloy, and 6% aluminum and 3% vanadium is mixed, and half alloy is almost half of the percentage what remaining are titanium. So these powder size and the shape is also very, very important. So normally the size of the particles will vary from say 40 to 100 micron size, and of course there are worldwide there are few suppliers, and I'm not sure India already they started producing, but still we are importing this powder alone, and the parameters very, very interesting to make how to do that work. And post processing is also very, very important, because the selective area is bed fused, the remaining powder is remaining there, so the powder has to be removed. Similarly, after the heat everything is over, you may be knowing any metal, if it is going through extensive welding or heat, this thing, lot of stress. So the stress has to be released. So we have to do a heat treatment. Generally, I used to tell to my engineer, they asked, why you do require stress relieving, sir? So maybe you can think of a farmer, is work night, daytime full from morning 10 o'clock to evening 4 o'clock, hot sun, and he gets stressed or so much work he has done. All his muscles are all stiffened and this thing. When he comes back, his wife prepares a very good hot water, and he takes bath and he relaxed. So the moment he takes the hot water bath, all muscles are reoriented to old positions or whatever you call it, and he gets a freshness. Same way, the metal, when you work, whether with the heat or bend or anything, the metal also gets strained, and the orientation of the fiber and everything is getting strained. So if you like our hot water bath for a man, here we put it in the oven, maybe around 1000 degrees Celsius or 900, and cool it in the air or open and other things. Slowly, depends upon the material, the stresses are all relieved. So definitely here also that is required. Since it is a powder, fine powder, sometimes there could be a small porosities or unburnt powders may be there. So we normally some recent advised is to go for HIP process, that is hot isostatic pressing. I think you may be knowing, like SIP or HIP. So in high temperature with high pressure, you keep the component, automatically it densified. So all the pores are removed. So such techniques also now available. So that also some places we will apply. So like that, we use all those things, and cleaning and polishing, all these things will be done. And some of the machining also be required for post-processing, like thread cutting. So maybe for an injector, I have to assemble a valve or anything. So I may require again a groove if it is a flange, or a thread. So that has to be done by a conventional machining further processing. And qualification is another big area. We will touch upon that. So as I told, there are many more techniques are also there. One is called cold spraying. Another one is powder fed bed fusion. This is the one widely used, and India it is main places, even in Bangalore or this thing, maybe in Bombay also, maybe that I'm not sure. And this powder bed fusion of high energy can be electron beam or a laser melting or laser beam. So these two are used in powder fed fusion. And another one is direct energy deposit. This is the latest one. This particular one, electron beam and laser beam, we require very important environment. It should be a vacuum, and you have to create electron beam and other thing. But if you want a huge components, it is very, very difficult to have. So now currently in US already they started a direct energy deposit DED process, where the powder is enveloping the gun or the source of the power, and it is deposited directly to the as a component. Here maybe I will a little later I will touch you can also take one of the project in DED. Maybe I will touch a little later. So the powder bed fusion, as I said, there is a powder, and the one layer maybe from 20 micron to 100 micron. So that much one layer will be lit on the bed, and your laser has a beam and it melts. You can see the component and this one. So like that, layer by layer, it is maybe about 50 micron, 50 micron, 50 micron, like that. Every fusion is completed, one layer of fresh powder will be put over that. Again, it will be fused. So that is the technique used in powder bed fusion. You can see this is in Pune machine for our own thrust chamber. We asked them to do a trial run, so they have completed. So you could see the other side, the powder putting the machine also is already there on the other side. So this is the technique. Laser is melting wherever we require. It will melt. The remaining portion it will leave as a powder. And the next one is the cold spray. This tried long back in ISRO also we tried, but we could not succeed much. But currently in DRDO they have a machine. It is though no environment is required like other one. So here the powder, like metal powder, you might have like coatings. So here also with the high gas heater and with the high temperature, the powder is melted. And one important thing is when it is ejected out, it is under very high velocity. So if it falls on your body, the impact energy is sufficient to bond. This is a very important technique we are also feeling, because now current, whatever we made in Skyroot, the engines are all very small size. If we want to go for 100-ton engine or 50-ton engine, the size will be so huge. The combustion chamber pressure also very high. The heat transfer is very big, high amount. These type of materials what we use like Inconel and other things cannot work. So we require inside a copper. So copper has to conduct very fast, but copper cannot take that much load. So we require inside copper and the groove, and outside again high strength metal. So double material joining is still in printing, it is not feasible. So what generally they are planning to do, the copper they will print first, then over that this cold spray they want to do it. This technique we are trying for our future requirements. And this is the direct energy deposition method. You could see the left hand side. The inner core is the laser. The outer is with inert gas with the blown powder. That is the powder and gas is blown out. So in the melt pool, it melts, and then it is like a welding, but there we will put a rod. Here also you can put, instead of the powder, rod also people used to make. So this is a way direct energy is, you could see the big divergent for bigger engines like 100-ton engine. Divergent is made by direct energy deposition recent ways. Otherwise, earlier techniques are you take the sheet and roll and punch and contour, all those things. Here only I said the JanyuTech can do. The above that you are seeing a small arm, but it is not a small arm, it is a robo. So that robo has to, whatever in the 3D, the contour and other thing, it will follow and it will deposit. So maybe you can take up as one robo can develop for depositing this type of gun. That will be more useful for our future requirements. This is what I want. So maybe you can ask what are the materials currently we use is aluminum alloy 6000 series magnesium and manganese, and Inconel 7-on-white widely used. We are also using 7-on-white. 625 also equally good, but the strength is not that high. So Inconel 718 currently. You may ask conventional bar and rods and other thing. If you are 3D printing, what will be the strength? Whether it will be a cast, like it looks like you are depositing. So casting is always very less. Here also it will be like that. No, because after the heat treatment, it is sometimes I have seen almost equal or even more also, or it will be plus or minus 5% to nominal values we are getting. So that is one of the very good thing. You can weld it, you can do whatever you want like any other material. So the printing is only helping, and the strength wise or the percentage of elongation, it is not at all coming down by this process. So widely we are using Inconel 7-on-white as well as 6Al4V and half alloy also we are trying to use it. So these are all the material property also. We have done extensive studies by taking lot of samples and putting in low temperature and high temperature, all these things, and we have a good database now for 3D printing. Sorry. And I will take one case study or this is one of the injector for our small engine. It can develop 850 Newton thrust. So you could, first one, you have to make a 3D model. It is nowadays all engineers coming out from any college, they can make a 3D model. And this is what I said, internally if you see, and center is for oxidizer, the N2O4 will come and bifurcate into two lines and then it is coming. I have shown it is not a circle, it could be on the top elliptical, because otherwise this is what I said, the design has to be properly made. And similarly in the side, right hand side, you see another pipeline. Through that fuel is coming. Again, it is all around, and you could see the orifices, and you could see the fuel orifices. This is the oxidizer orifice. So the orifice sizes are in the order of about say 1 mm or 0.8 mm. That also can be easily, that particular hole alone, the powder will not be melted. We had a lot of problems, like because it is when it is made at heat is so high, when the heat is reduced, the shrinkage factor will come. So if you want 1 mm, it may be becoming 0.8. So we studied a lot. We cut the specimen, how much it is going and all those things. So now we have a handle, what you want, how much you have to give in the drawing. So this is also one of the design criteria, how much shrinkage is taking place in this place. So this also we have studied and we have done wonderful thing. You could see this is an injector one third we have cut view. You could see internally how the propellant in different places. That's why I said earlier, we might have done many pieces and welding and all those things. Now it has come in single piece. So when we are talking about design, you could see one flange, if I put, some supports are required. Otherwise, that will not separately stand. Later, the support can be removed. So the removal of the supports, it should be minimum possible. So the DFAM study we used to carry out. And this is the one I said that after completing the process, we will do the heat treatment. So the heat treatment is very, very important, and it has to relieve the stress. Otherwise, what will happen is sometime, if it is a thin structure, warping can come. So to avoid that, you have to do heat treatment and this one. If it is required, we can go for hip also. But currently we are not doing hip, but heat treatment itself is giving a very good strength and very good this one. And this is all post-processing. We have to remove all the structures all around. Maybe I will show you later how the structures are built, how much we have to remove. Then conventional machining also we have to do. So finally, this is the product. We got the groove machining and the thread machining. These two are conventional machining we have carried out. You could see the surface finish, and we could get approximately maybe around 0.8 micrometer in RA. So that's okay. If you are doing a machining, you may get a better finish. I'm not telling, but outside it is not required that much. So it is okay for our requirements and other things. So we are going ahead with this one. This acceptance we are planning to do is we used to do a water calibration, because the orifice is the main for especially for rocket. So you could see as printed, we have not again drilled the hole or anything. We could get beautiful jet we could get. And another one is left hand side. What you are seeing is the cryogenic engine. It is 3000 Newton, and we have done digital radiography or CT scan, whatever you call it. We could see the grooves. This is a double wall, and all the grooves, because we want to check whether any blockage is there, and even in one or two cases, minor blockages were there in few channels. Okay, I took a decision. It may not problem. We can go ahead and we can do the work. It does the work. So clearly, you could see CT scan left hand side, and this machine is available in DRDO, and they have done it lengthwise. It is like our human brain or anything you want to do CT scan. Same way, we did it, and we could find out any flaw is there. So you could see as printed, we are seeing all around these structures, that is support structures, that should be removed. And bottom also there is a plate. From the plate only it was built. So that plate and all the whatever you are seeing in the line, that also has to be seen. Now after that you could see how the engine will look like, and after moving. So these engines, finally we hot fire. Before we, you could see one of the divergent. We took lot of time to make this divergent with highness 25 alloy, because when you go for super alloy, when you make this type of contours, or at least 3-4 times you have to do heat treatment and improve the flexibility and all those things, then only it will be formable. So almost like 2 months it will take. But this particular component takes only few days. Our printing is only 3 days or 2 days, and only heat treatment and cleaning and machining, all those things only take another 1 week or 10 days time. So this thrust chamber also we have tested already in our test facility. And only one area is, this is a process controlled thing. Once if you set everything, powder started, and even inside online defect detection. Currently, some of the machines, now India no machine is having this kind of detection. So defect detection is one of the very big question mark today. How to detect? So there are a lot of gaps, because if you take the powder size and the shape is very important. Moisture content, even minute content of moisture lot of defects can come. So we have to be more careful on the feedstock. So it has to be properly stored and all those things. This is one of the important thing. Second one is the process parameters, variable numbers in your generating power, vacuum, this, that, and movement of the gun, everything. So once it's set, fine, it will make even numbers, very high numbers and other things. So there are certain gaps. And currently worldwide, suppose if you take welding, we have so many acceptance norms, how much it should be there, mismatch is how much, and what are the defects, how much bigger size you can accept, what is the minor pore we can accept, what is the maximum pore, cluster pore, all are already documented. But in this area, we are only starting, so not a good level of acceptance is available. So we do by water calibration or hot test and other thing, then only we accept for this. So this is one of the engine. So we did with liquid oxygen and LNG. First time in India, of course, I tried this combination, and and this engine was tested at Nagpur, and you could see the logs first is going, and we tested this engine very successfully for 200 seconds in Nagpur facility. This is that you could see the inlet is like LNG is flowing, and then it is coming out, and then it is going back. So the valve, whatever you have seen, is only for that. For bigger engines, inside it should be copper. So that technology only we are trying to make. This is a hypergolic propellant. That also we made only with Inconel 718. And this is tested at Mahendragiri near Kanyakumari. And you can see the background, lot of windmills, and this is also very perfectly tested. Now currently we made our own test stand, and we are doing at Hyderabad, this hypergolic propellant. And these are all 3D printing what for the last 6 years I could learned a lot. So I want to share to you and what are our things I have for the last with my engineers we have developed, and we want to share with you. Maybe in your area, if any critical items are there, in my opinion, 3D printing is the best way of doing it. Thank you very much for patiently listening to me.
You talked about process control, etc. Is it possible for us to build digital twins for specific steps in the process and then improve the modularity and scalability of 3D printing? That's my question.
The problem is all machines, it is all imported. No one wants to touch, or I would say it is slowly. I think one machine with Pune, he himself developed. So he is trying to do improvement and other thing. What you said is really correct. I think most of the parameters. Only why I said this parameter, you can fix the power and other thing. In case if your product, some places it is thin, some places it is thick, then the thermal behavior while welding is different. So internally the stresses are coming. So currently what they are trying to do is image with infrared thermography. Sensor has to be inside the place where the printing is taking place. So the sensor development itself is still not at come to a point. Okay, you can make the digital way all the input parameters. Process at the time of taking, how much defect is coming, how to control. The feedback mechanism is lacking.
The reason why I asked this question is because of twofold, or maybe I can quote 3 examples. One example is we have built a digital twin for the furnace also in a steel mill. For example, Tata Steel Mill, etc. in UK and Netherlands, etc. We have done it, number one. Number two, we have done what is called the computer vision based, or whatever you want to call it, with respect to non-destructive testing, because you talked about the moisture content, etc. So non-destructive testing is the second one. Third one is in the healthcare, we are aggressively working on what is called the biomarkers for cancer screening. It could be lung cancer, it could be skin cancer, it could be blood cancer, it could be whatever. So we are working very closely with different healthcare organizations and, for example, pharmaceutical companies, etc., where we are not only looking at the sensing aspect that you touched upon, because we have specifically built solutions on what is called quantum sensing. We have done it in the oil and gas industry. So we have looked into quantum sensing on the sensor side. we have also looked at extensive database systems for what is called the health screening for the biomarkers for the cancer. That also we have done. So
Sure.
I think there could
We
be
can,
potential
Maybe
areas
I
of
will ask
discussion
our
that we can
Amit
have.
to talk to you. Yeah, that will be
Yes,
nice.
yes, please.
Yeah.
Sir, if you are okay with it, then maybe I can reach out to you through JanyuTech, and then we could see how we can work together.
Sure, I will be very happy. I will be very happy to improve the system in our workplace. Definitely.
Okay. Thank you, sir. Thank you,
I
sir.
will also be very happy. He is my close friend only in Pune. I'll ask him. We will have a common meeting. You can tell your thing. We can, if it is possible to incorporate quickly, we will do that.
Sir, Hemant sir, not a question per se, sir, but really wanted to just thank for the presentation and sharing all the observations in great detail. And we wish all success for the launch. We all look forward for very soon a private company from India placing a satellite in orbit. So we all are really looking forward to that. And if you could share some detail, of course, today the topic is slightly into 3D manufacturing, but if you could share some detail of the launch vehicle and what is being geared for launch.
Maybe it was, I didn't plan, otherwise I would have, maybe I can tell right now, but if you want another meet, I am ready to show what is our first stage, second stage, third stage, how all the details I can share with you. Nothing wrong. It's only maybe after 1 or 2 weeks, whenever it is free, I will explain.
Definitely,
sir. This is Arun here again. I was fortunate about 4 or 5 months ago to visit the IIT Madras Tayyur campus.
Okay.
Where if I may use the word, your competitor building the 3D printing. Professor Satya Chakravarti is my classmate from IIT Madras.
Okay.
And the ex-ISRO scientists, etc., esteemed professionals like you.
Yeah.
So they have helped them with respect to launch and 3D printing and things like that. So I could see all the, I could touch and feel all the parts. It is not just, talking on the computer. I will reach out to you through JanyuTech and we will be in touch, sir. Thank you.
Sure. Thank you very much. Because this is one of the fast developing fabrication technique. And maybe I especially some of your robotic arms and other things, high strength titanium to be fabricated. This is one of the easiest route to do that. That is my opinion. Maybe I don't know the components size and other things. We can easily print it. Plus, currently Pune gentleman, that company where I am going, he's making composite printing also. So that composite printing strength also slightly high. So maybe some of the areas you can think of replacing the metal to composite. That also very unique shape and other things it can print. So that also last visit I have seen. Maybe I can share the number. Anybody is interested, kindly visit and they can provide all the requirements.
Definitely, sir. And
especially youngsters, now you can think of many components to be fabricated by 3D printing route.
So we in fact make some of our robots in 3D printing, sir.
Oh,
some components, the chassis, etc. in composite 3D printing this thing, but it is more for all-terrain vehicles as of today. But we are in the process of making a robotic arm for high temperature, around 1000 degree temperature level application. So I think we will definitely require
1000 degree very easily. Now one super cool powder is there.
Okay.
In Navoda, near Noida, Delhi, one of the printer he is using. Highness 25 powder he is using. Highness 25, even Vikas engine divergent is made out of KC20WN, which is equivalent to Highness 25. That is a French norm. This is the American. So this HS25 can withstand up to 1200 degrees Celsius. So that powder, whatever maybe the shape you want, but the only thing is size. Now currently in India, the bed fusion technique or deposit, size is available 400 by 400 by 400, not bigger than that. So the size should be around 350 by 350 because you have to leave some gap for this one. Yeah.
Right. Sure, sir. We'll discuss with you on the specifics of the engineering.
Sure. Anytime you can call you whatever your requirements. I can connect with somebody if you are interested. I'll talk. One more good product manufactured in Bangalore is Vero Metal. They are also this last chamber what I have shown is made by Vero Metal. Inside the channel is a helical channel. Very nicely they have printed last 6 months back. So somebody asked what is the status and this one. This month end or beginning of next week or in month end itself I am planning the final 4th stage integrating with main engine and 450 Newton and all these things as a stage. I am planning to do a test. After that only flight maybe the next time when you are calling I will explain all the details in detail. Thank you. Thank you very much.